So today we're going to talk about memory allocation, in particular allocating kernel memory. We look at two strategies of doing so. As you know that the kernel needs memory for very frequent or frequently happening events. Whenever you execute a program, for example, that's creation of a process for which the system must maintain a particular data structure for that process. And for that, it needs memory, the task underscore struct, right? And this structure is of well-known size, correct? Which means the kernel, okay, most of the time, it requests memory of well-known size, okay, well-known size. So it could be, for example, a struct to host a process information, or a struct to host information related to memory, or information related to a device, and so on. These are well-known data structures that we have shown you at the beginning of the semester. A set of data structures that are used by a particular operating system. And we need to allocate memory for them, okay, or the kernel needs to do so very frequent. Memory can be allocated. Here we look at two different strategies. One of them is called the body system, and the other one is by using slabs. Okay, so first we talk about the body system. A portion of memory with a particular size can be used for such allocation. However, the allocation of process is done in this way. Having a request which is rounded to a size of powers of 2. Rounded to a size of powers of 2. So if the request is 30, then it's rounded to 32, for example, right? So that we can write it in terms of powers of 2. And then the request becomes, okay, memory size 32 units of memory, regardless of what is that unit, okay? Byte, kilobyte, and so on. So having a request of powers of 2 and having an already existing memory again as powers of 2, what we're going to do is to divide this memory into two halves. Divide it into two halves. So if the original memory is 2 to the power k, then when you divide it into two halves, you're going to have two portions. One is 2 to the power k minus 1, and the other is of the same size, 2 to the power k minus 1, right? Okay. And then we look at this power, which is 2 to the power k minus 1. Does it satisfy the request, the requested size? If it does, then what about dividing it again into two halves? Will that size satisfy or no? If yes, we're going to divide it again and again until we no more can divide this memory into halves, because we're going to get a size that is less than what is needed, okay? So the concept is like this. For a request of powers of 2, allocate a block of memory of powers of 2 that is the smallest that can fit the request. Smallest that can fit the request. Okay, so I think the example make it much simpler. Okay, so if you want to allocate a block of size S, the very first thing to do is to round that to powers of 2. So we write S in terms of powers of 2. For example, 2 to the power I. Then we look at the memory that we have, okay, and try to fit this request, which is 2 to the power I. In fact, the mapping of this memory and how is it partitioned is always kept in a data structure similar to this. We have a list, And in this list, we show portions of memory of powers of 2 and how many of these portions are available. For example, if I look at this list, I would find that I have one portion of memory, one block, and the size of it is 2 to the power k. However, I don't have any block of size 2 to the power k minus 1, right? And here I have 4 blocks of size 2 to the power 2, and so. Which means looking at this list, we would know whether we have empty blocks of certain sizes or not, and how many of these blocks, right? Okay, so the map of this, showing the allocation and the sizes of blocks of memory, we can read it from this representation, correct? Okay, of course, these two, they don't match in here. Okay, they are general things. Okay. So now, let's have an example of allocating a 100 KB, okay, 100 kilobyte. At the very beginning, this is the memory that we have, and we have a request of 100 KB. So the 1 mega can be divided into 2 portions, right? Because the 1 mega is much more than the 100 KB. Now, if this portion is more in terms of size than 100 KB, then I will commit this kind of dividing the memory. So I will have 2 portions. Okay. And then I will take one of them, one of these 2. Okay? So if we take the one that is the highest, then we have to keep doing so, take the highest. If we take the one that's the lowest, we have to keep doing so. So we have to be consistent in the algorithm. So here we're taking what? The highest memory. Highest memory now, if we divide it into 2 and we look at the size, we find that it is also greater than the 100K. So what do? We commit this kind of dividing the memory, right? And then we divide it again. We take the one to the left, which is the highest, divide it again into 2 halves. So 128, 128, still more than 100 KB. It can fit, right? So we commit this operation. And then we look at the highest, one of them, which is the 102K. We think of dividing it into 2 halves again, which is 64, 64. However, 64 is less than the request. So we don't do so, and we allocate the 128 block for a request of what? 1 kilobyte. As a result of that, we have what? Internal fragmentation. Internal fragmentation. So, and also, as a result of this, we have the memory being divided into different blocks, okay, of different sizes. Okay, we had only 1 block, and as a result of satisfying this request, we have 4 blocks, 3 of them available, and 1 is used. This has to be reflected on the list. Okay? We look at some other requests. So this was the request that we looked at just now. Okay? Now suppose that we have another 200K block to be allocated. So we know the blocks that we have and their sizes. Okay? So the 200K, you put it in terms of powers of 2 to the nearest. Okay? And then we find that actually we have 256 which can fit it. Right? And then based on that, we do what? The fitting. Now, suppose we have another 200 kilobyte. If we look at the list here that represents this, okay, we will find that we don't have, okay, the 256 block that can fit the 200. So the only option is to look for bigger sizes of block. And how bigger? If my request is 2 to the power I, then I will be looking for blocks of size 2 to the power I plus 1. Okay? And I have 1, which is 512. So now we divide this into 2, and then we use one of it because it is the one that satisfies the request. So as a result, we have this. We have now 3 blocks used of different sizes. Okay, this is of size 128, has internal fragmentation of 28, and we have 2 blocks, each of size, not the size of the block. The size of the block is 256. Okay, but the used is 200, so we have 56 as internal fragmentation for these 2. So you can find a total internal fragmentation here. As well as we have 2 empty blocks of size 128 and 256. Now suppose that we have another request again, 130 kilobyte. 130 kilobyte, then you have to round it to powers of 2. Basically, you will need what? The 256 partition, right? And we already have one. Then we would use it in here, and we will have, of course, more internal fragmentation. Okay? 130 is very near to 128, but it is what? 128 cannot fit it. So we choose to have, now increase the powers. We increase what? The powers. We're doubling the size of the partition. So 256, which means the internal fragmentation is a lot, right? However, this kind of allocation is fast. Maintaining and managing the memory using a list like this is very efficient, okay? And the most important thing, compaction process, which is joining back partitions of memory to form bigger blocks, is also easier to achieve. Easier to achieve, because we have everything in terms of powers of 2, and we know the addressing in there, and then we would know whether 2 partitions are adjacent and belonging to the same parent partition or not. Now, why we call this buddy system? Buddies, okay, they're close to each other, isn't it, right? So basically here, buddies, we say 2 blocks here are buddies if they belong to the same parent partition, if they were a result from a bigger block. For example, in this case, if we are to free, suppose that we are to release here, suppose that we have to release 200K, this 200K, okay? Then the system will claim back a 256, right? Okay. Now suppose that we are freeing again another 200K, which is in this block. The system will claim back another 256. Now these 256 blocks, they are next to each other, okay? But they are not buddies, because they were not a result of partitioning a single block, right? However, if we have this freed, this 100K freed, then this 128 claimed back block together with the one next to it, they were a result of one bigger block. And by that, they will be joined. And joining them will result in a 256 block that can be joined also with the one that is next to it to form a 512 block, okay? So the system automatically, I mean, in an easy way, okay, will be joining buddies, okay? Why do we do that? To avoid a concept that we call what? External fragmentation, right? External fragmentation. Now, the other way of allocating memory to the kernel is by using the concept of slabs. Here, we have 3 terms: slab, cache, and objects. We have a cache, basically, is a portion of memory, okay, that consists of number of slabs, where these slabs, each one of them is a block of contiguous memory. Block of contiguous memory, that's the slab itself. And the slab is divided logically into fixed size partitions. Each one of them is called object. Each one is called object. a collection of slabs, they form a cache. We have various types of objects. Each one of them is meant to fit a particular kernel memory requirement. Okay? A particular memory requirement for the kernel. For example, we could have type of objects to fit the memory requirement of allocating task underscore struct size, okay, of memory for the kernel. And that's frequently needed. And we could have another type of objects that is enough to allocate memory for a struct to hold information about a particular type of devices. Okay? So objects of different memory requirements of different sizes. Objects grouped together in a slab. Slab is contiguous memory. Various slabs are grouped together to form a cache. Okay? But under one cache, we have objects of the same type. Okay? So we can say we have different caches, okay, each one of them to serve requests of different sizes of objects or different types of objects. So the idea is like this. We have kernel objects of different sizes corresponding to memory requirement, okay, needed by the kernel. And then these are basically within slabs, and a collection of these slabs formulate what? A cache. The slabs themselves, they don't need to be adjacent, okay, or contiguous next to each other. But when I say a slab, I mean what? A portion of memory, okay, that is contiguous. A range of memory that is contiguous. Different portions of contiguous memory, which means different slabs, they formulate a cache. Okay? And in each slab, I have a number of objects. So the idea is like this. Whenever there is a request from the kernel, then the size of that request will determine which cache to access. Because certain caches, serve certain number, certain sizes, right? Certain type of objects. Now, if we have slab in the cache, then we look at the objects within this slab. These objects are marked either free or used. Which means initially, okay, these objects, they're already known. The size of them is what? Known. Memory is allocated already of certain size. However, it is marked either free or used. Now, if we can find a free object, then that will be for satisfying the request of the kernel. Okay? And we're going to change it to be what? Used, after satisfying the request. If we can't have that within a slab, then we look for another slab belonging to the same cache. And when we look for another slab, we look at a slab that is partially filled. Partially filled means it has some objects that are used and others that are not used. If we can't find so, then we look for a totally new slab, okay, and we allocate one of its objects to the kernel as requested by the kernel. So that's called slab allocation. Do you have any question about slab allocation? Any question? Do you have any question about body systems? You can do that? Yeah? Okay. Since you can do it, let me, having this table, okay, on a piece of paper, okay, right, assume that you have what? A memory, and the size of the memory is 2 megabytes. 2 megabyte. Make it smaller. Wait, let us make it smaller so that you can really do things nicer. Okay. Let's say the size of the memory is 4K, 8K, 8 kilobyte. So that you can construct the list. 8K. Okay. So that's the body system. 8K. Draw the list or the final list showing the memory after allocating the requests (256 bytes) and 1 KB, 1 kilobyte. So now you have to draw a list of how many entries? How many entries in your list initially? What's the shape of your list? You have entries in here, right? 0, 1, 2, 3, and so. Correct? Now this will correspond to a 2 to the power 0, 2 to the power 1, 2 to the power 2, right? 2 to the power 3, and so. This is your list. Initially, what you have, only one of 8 KB, which is 2 to the power 13. Okay, 2 to the power 13, which means this is 13, corresponding 2 to the power 13. How many blocks you have? 1. So this is the initial, okay? Initially, this is what you have. Okay? From 3 up to 13. Now you have a request of, you mentioned 256, right? 256. 256, we need to write it in terms of powers of 2. Here we have an exact of it. Okay? 2 to the power 8. So it is 2 to the power 8. Sometimes you don't have an exact of it. For example, if I say 200, okay? Then this one you have to write it in terms of powers of 2. So you'll have to go for 256 as an approximate of that, right? So again, here you're supposed to have this. Okay? Got it? The rounding. So if you go to 256, how can I look it up here? Basically, you don't have to search. You just go to the entry of 8, right? So I have here 4, 5, 6, 7, 8, 9, 10, 11, okay, and 12. And do we have anything there for 8? We don't have. It's null. Okay? So we don't have of 8. Then we don't have of 2 to the power 8, right? partition. So then we look for what? 2 to the power 9, which is double of 2 to the power 8. Correct? Do we have? We don't have. Then 10, 11, 12, 13. Correct? We have? Yes, we have. So what are we going to do? We're going to divide it into 2. If you divide it into 2, that means you don't have this anymore. But you're going to have 1 of 12 or 2 of 12. But your aim is to get 1 of 8, right? So the 2 of 12, you're going to use 1. The other one, you will leave it here. So what do you have? 1 of 12 here. The other 1 of 12, you will divide it into 2 of size 2 to the power 11. You're going to leave 1 here, right? And then the other one, you will have 2 blocks of 2 to the power 10. You're going to leave 1 here, and again. So when we reach in here, 2 to the power 9, we're going to leave 1 here, and the other we're going to divide it into 2 of 2 to the power 8. We're going to use 1 and leave 1. Right? Correct? So this is how it should look like, okay, for satisfying the first request. The second request is what? 1 kb. So your 1 kb here is 2 to the power 10. Okay, so you round it here, and here you have exact 2 to the power 10. Do I have 2 to the power 10? I have. Then what should I do? Just remove this. Use it. Correct? Do we know how to draw this? Okay? Now, having this, can you draw the memory? How does it look like in terms of blocks? We should be able to, right? Should be able to. Can you? Do you want to try that? Try to sketch it. Sketch the memory that corresponds to this list. So the whole thing is of size 2 to the power 13. You have what? One of it, which is 2 to the power 12. And you have another one 2 to the power 11, right? Which means you get this. This is 2 to the power 11. Remember that when we allocate, okay, we use the highest, right? And then, do you have 2 to the power 10? I don't have. But I have 2 to the power 9. But 2 to the power 9, how many I have? 1. 2 to the power 9 is actually a result of dividing 2 to the power 10. Okay? So if I say I have 1 2 to the power 9, okay, and I don't have 2 to the power 10 of their bodies, means this is what used. Right? Isn't it? Or this is used. Now, depending on which the allocation done first. But in fact, what we did, we used this. We used this one, right? We used left, based on the way that we did it. So this is what 2 to the power 10 that had been divided into 2 of 2 to the power 9, right? So we have 2 to the power 9. One of them, okay, is there. So this is 2 to the power 9. And the other one had been divided into 2 of 2 to the power 8. One of them is used. So I have here 2 to the power 8, okay? And this one is what? Used, okay? There is much more about this, in fact. We can program this, okay? You hit programming, I mean, at this stage, because we're busy with some other programming stuff, right? But we can program this, okay, and take advantage of memory represented as powers of 2, the blocks of memory here. And if we look at it carefully, we can actually decide whether to join adjacent blocks or not. So we can find the relation, okay? If we look at the binary representation of these, we can find the relation, okay, and use it to judge whether 2 blocks are bodies or not. Only by looking at the bits, okay, at the bits representation of these blocks, okay, and that's why it is fast, okay.